In the last video, we set up a whole bunch of different limit properties, and we wrote down some rules that are really going to help us evaluate different limits when we see them in the future. And so what I want to do in this video is I just want to do a few examples of different limit problems that you might see that sort of demonstrate these rules, I guess. And in doing that, maybe we might even come up with sort of new addendums to these rules that we set up. So anyway, let me actually go over here and go over to a new spot. And let's actually do an example. And this is going to be a pretty straightforward example that I think we're probably already going to know the answer to. But let's do an example that's going to demonstrate the first three properties of limits that we set up in the last video. And this one's going to be pretty straightforward. Let's just say we were taking the limit, we had a function, and we were taking the limit as x approaches, let's say 2, of the function x plus 1. And so now, with our intuitive definition of a limit, that the limit is saying, well, what is this function approaching? This function is x plus 1. And what is that function approaching for what is that function approaching as we choose values that get really, really close to this value 2 right here? And so we sort of already know what this is. And this function is just going to look like a line if we were to draw it. And we know that every point on that line is kind of being approached to by the point right before it and the point right after it. That it's a completely continuous function. There's no reason we can't plug any real number we wanted to into this function and just sort of get the answer. So we sort of already know what this function is going to be equal to. We could just take 2 and plug it into this function and get the answer. But what I want to do in this video is I just want to show you how we can sort of break this function up and sort of demonstrate those limit properties that we talked about in the last video. So we can say, because we know that the limit, that we've got a sum of two different functions. You can sort of look at this function as a limit of the function f of x is equal to x, and the limit of the function, let's say g of x, is just equal to 1. And we can actually rewrite this and sort of distribute our limit operator as the limit as x approaches 2 of the function x plus the limit as x approaches 2 of the function 1. And so now we have really got, just staring us straight in the face, the first two properties of limits that we talked about in the last video, where we see that if we took the limit of some constant, we would just get back that constant. And also, if we took the limit of just the function x, we would get back whatever the limit was approaching. So let's just go ahead and we can just work with those rules to evaluate this limit. So we've got the limit of as x approaches 2 of just the function x. And so we know from our limit properties that this is just going to be equal to 2. And that this function, the limit as x approaches 2 of the function 1, and you can think of this as just a horizontal line along the line y is equal to 1, or along the line f of x is equal to 1. And no matter what x is or what x is approaching along that line, that function is just always going to be equal to 1. So to get the overall limit, we just add these two things together, and we get that this limit is equal to 3. And this isn't really surprising. We could have seen this from the very beginning, that this was just a continuous line, that we didn't have any points of discontinuity. There weren't any points on this line, or there weren't any x's on this line that we couldn't just plug in. If we were looking for the limit as x approaches 1,000,000, we could have plugged in 1,000,000 and gotten 1,000,000 plus 1. And if we had been looking for the limit as this function, or the limit of this function as x approached pi, we could have put in pi in and gotten pi plus 1, and it would have been 4.14159 whatever, whatever. So this wasn't really a surprise, right? We just used our limit properties to break this up into the sum of two separate limits. So anyway, was our first example. Just write ex1 up there. Let's go ahead and let's do a second example. Example 2. And so in this example, we're going to take the limit as x approaches, let's say x approaches 4, of the function 2 times x minus 3, let's say. And so now you're probably thinking, well, there are a number of things that we could do here. We could just say, you know, if we had the function, if I just gave you this function, we said f of x is equal to 2 times x minus 3. If we were going to put this into, I guess, mx plus b, into slope-intercept form, and you were going to put it into a form so you could really easily and very obviously graph this function, you would probably multiply this 2 into these parentheses, right? And you would get 2x minus 6. And that's a perfectly reasonable thing to do here. But what we're going to do in this function is we're actually going to use the fourth limit property that we talked about in the last video, where we said the product of two limits, the product of the limit as x approaches a of f of x times g of x, that was going to be the same thing as the limit as x approaches a of f of x times the limit as x approaches a of g of x. So let's go ahead and use that limit property to evaluate this limit. And what we're going to say is that this 2 right here, that this is going to be our f of x part of the function. And this x plus 3 term over here, this is going to be our g of x part of the function. So if we wanted to, we could have just sort of multiplied this 2 into the function and gotten 2x minus 6. And we could have evaluated the function more or less the same exact way that we evaluated our limit in example 1. But in this example, what we're actually going to see that we're able to do is we're able to rewrite this limit of a product as the product of two separate limits. So I'm going to rewrite this as the limit as x approaches 4 of just 2. That's going to be our f of x function. And then we're going to multiply that entire portion times the limit as x approaches 4 of the function x minus 3. And hopefully you can see that based on the last video, we've got our example. And actually, I'm just going to erase this down here because we don't really need this anymore. There we go. And so hopefully you can see that right now we've got our same property where the limit as x approaches any number of just a constant is going to be equal to that constant. We've got that property staring us right in the face now. We've got the limit as x approaches 4 of just the constant 2. So that's just going to be equal to 2, right? So it's almost like we just pulled that constant out. And even let me go ahead and I'm just going to rewrite this term right here. I'm just going to rewrite the limit as x approaches 4 of x minus 3 right there. And so now we've sort of realized a neat, you could almost call it a new property of limits, where if we have a limit as x approaches some value a of some constant term times a function, of some constant term times some function f of x, that we can just pull this constant term past the limit. We can just say that this is going to be equal to whatever that constant k is times the limit as x approaches a of f of x. So that's a really powerful tool that we're going to be using in a number of different ways. And again, you can see that we're sort of simplifying the term that we have to take the limit of. So anyway, now let's go ahead and just finish up evaluating this. And if we wanted to, we could break this function up into saying that this was equal to the limit. Actually, you know what? I'm going to go ahead and do that. So I'll say that this was sort of our aside. That was sort of we could call that property, 4a of limits, even though that's looks kind of bureaucratic, I guess. But anyway, let's say, so now we can keep on going with this example. We can say that this limit over here, that's going to be equal to the 2, which was the constant that we pulled out in front of our limit. And let's just go ahead and distribute this limit into our sum again. This is going to be equal to the limit. And I know that I said sum, and we've got a subtraction sign here, but it'll work the same exact way, that our limit sign can distribute over a plus sign or a minus sign. We can rewrite this as the limit as x approaches 4 of just the x term, in parentheses, minus the limit as x approaches 4 of just that 3 term. And so now this is in sort of the simplest form where we can take this limit. And we get 2 times the limit as x goes to 4 of just that term x. That is going to be 4 minus, and let me put all of this in, should have had those parentheses like that around that term right there. So we're going to get 4 minus the limit as x approaches 4 of just the term 3. That's just going to be 3 right there. So we get 4 minus 3. That's just equal to 2 times 1, which is just equal to 2. So anyway, there are, I guess, 2 examples of pretty simple limit problems. We might do a few more limit problems that are sort of this simple, that really are just, plugging the numbers into these functions, just to demonstrate these concepts of limits. One of the really important takeaways from this video is this new rule that we sort of developed, where if we have the limit as x approaches some value of a constant times a function, that we're going to be able to just sort of move that constant out in front of our limit, or we're going to be able to move the limit past the constant, either way you want to look at it. So anyway, I guess that's it for this video. Thanks so much for watching, and I'll see you in a future video.